What we're trying to do is we've got solutions of trigonometrical equations. So where we've gone is we're going to go back into solutions of trigonometric equations. I'm going to start off on this and then I'm going to review some of the subchapter afterwards. What we need to do is we need to solve the equation. So you're going to be given an equation later on, and we'll need to actually graph that. Now, it's pretty easy to find solutions of graphs. So for example, if you've got sine theta, well, hopefully you can remember that's just a measurement of the y-axis, okay, because sine is opposite over hypotenuse. So when you do have that, hopefully you can just recall that that is where we are. So when we've got sine, remember sine equals opposite over hypotenuse. And because it's a unit circle, that's 1. Sine is opposite, and cos equals adjacent over hypotenuse. So cos is your x, sine is your y, because it's how far up and down we are. So if you think about where we start on a unit circle, we start here, and then we move around, right? Oh, and we do a full circle. Now we start at 0, and then we end up at 1, back to 0, 1. So if you think about in terms of radians, we start at 0, and we end up at 1 at pi on 2. And then we come back down to 0. Sorry, at pi on 4, and then that ends at pi. And then we come down to -1. And then we go back up again. Oh, I'm pressing the wrong pen. So you'll get a graph that will look like this. Oh, wow. Ryan will be impressed with this. Oh, I just stuffed it up at the end there. So if you think about this, oh, come on. Don't have the biggest digital pad in the world. That's where we'll be starting at the origin. That's not really the origin. This would obviously then be pi on 2. So this is for sine theta, right? And this will be pi. And this would be 3 pi on 2. And that would be 2 pi when you do a full revolution. Now, hopefully you recall from last time, if I put a 2 in front, well, it changes the period to pi. And that means this is now going to be all compressed. So I just need to now divide all these by 2. So that would be pi on 4. That would be pi on 2. That would be 3 pi on 4. And that would be 2 pi on 2, which would be just pi. So when we do that, when we put a number in front, so it gets squashed, right? So hopefully you can recall about the dilation. Now, it's pretty easy to do those. Again, you know, I could have something like sine bracket, you know, I could have 2, and I could have like theta plus pi on 2. Now that's actually translated the whole graph pi on 2 this way, right? So we're going to move it to in the negative direction, right? So that's going to move it all there. So your axes would actually sort of now come through here. So that would now be 0. That would be pi on 4 minus pi on 2. Would that be negative pi? This would be, that was 0 minus pi on 2. So this would be now negative pi on 2. Pi on 2 minus pi on 2 would be 0. 3/4 pi on 2 minus pi on 2 would now just be 1/4 pi. Pi minus pi on 2 would be now pi on 2. So you can see that sort of translates the whole graph down. So these are pretty easy to figure out the x-intercepts. All right, we're going to be looking at these. We're going to be looking at the transformations and that too. The problem is if you start like adding things, okay? If I start adding a number, I mean, this shifts everything up by a half. So that means your graph now is going to sort of, your axis is going to come through here. The problem there is, what are these intercepts now? And that's where it gets a bit tricky, So normally when you've got like no vertical translation, it's not bad. You can pretty much graph the graph from understanding dilation, reflection, and transformations, and you can find your x-intercepts. You know, even if you had an amplitude, it wouldn't matter because you can still find your coordinates of those. Because obviously at the moment, if I put a 3 out here, that's going to be, instead of that being 1, you know, that's going to be negative pi on 4, 3, right before it was 1. So, you know, you got your dilations from your y-axis, you've got your dilation from your x-axis, you've got your transformation in your x-axis. Transformation in your y-axis is a bit different. So if you had something like that, that changes the ball game, how we go about solving these. And where I'm going is this solutions of trigonometric equations is what we want to do. We want to try and understand how we can do that to figure these out. Okay, so what we actually do, long story short, is we just basically let this whole thing equal x. We just say, hey, let's just equal x. Let x equal, 2 lots of theta plus pi on 2, and then we sort of figure everything else out. So you still might have your plus a half on here, plus 1 on 2, that is. Then, your equation becomes 3 sine x plus a half. And then what we do is we basically, we say that's what y might equal. And then what we want to do is we really want to solve this now. So, you want to find your x-intercept, so we're still at y equals 0. So it's going to be like negative a half, and then 3 sine x. You're going to divide by 3 and so on. That wouldn't be 3, that wouldn't work. But now I can actually look up sine values when it equals negative a half, because I need negative a half for sine. What that would be, I can list it all down. This is a general outline of where we're going for everything. This is all 3 sub-chapters together, so don't worry if you're a bit lost now. So let's just say this is the case. So really we're saying, hey, when does sine give you a value of negative a half? Well, if you recall, when a negative a half is, remember we do the equilateral triangle in here. We halve that because that's 1, 1, 1. So that would be 1 here on 2. That would be 30 degrees. That would be 60 degrees, right? So a half would be when it's pi on 6, right? So we know it's a pi on 6 when it's a half, but it's a negative a half. So it's actually going to be, if you think about it, here and here on the inner circle. Right, so it's going to be the list the values. Well, x could take on this, where you got to look at your domain and range, but let's just list a couple. It could be negative pi on 6. It could also be negative 5 pi on 6. So it could be negative 5 pi on 6. It could be negative pi on 6. Then that's going to be 6 pi on 6, 7 pi on 6. And then that would be 12 pi on 6, so it would be 11 pi on 6. And so on. So that would be where your intercepts are for sine x plus a half. But remember, x equaled, when we originally did it, 2 theta plus pi on 2, 2 theta plus pi on 2. So remember, x equaled 2 theta plus pi on 2. So that equals all these values. So I'm giving you like this is probably the hardest section where we're going to get through this week. So that would equal that. Now what I've got to do is I've got to minus pi on 6 from each of them, because we, sorry, it wasn't pi on 6. I think it was pi on 2, wasn't it? It was pi on 2. Now we've got to minus pi on 2 from each of these. But if you think about what pi on 2 is, we can actually change that, because these are all in units of 6. We could make that 3 pi on 6, which is the same thing. So what I'm going to do is I'm going to minus 3 pi on 6 on this. So it's going to be minus 8 pi on 6. It's going to be minus 4 pi on 6, which actually converts to, it doesn't matter, we'll do it later. That's going to be 4 pi on 6. And this one, 3 pi minus 11 pi on 6 would be, I changed the denominator to make it easier for subtraction, because I can see that in advance, 8 pi on 6. And then the last thing is to divide now everything by 2, because that's going to help undo the period from the dilation. So that is, now if you divide everything by 2 or times it by a half, it's going to make everything pi on 12, right? So it's going to be minus 8 pi on 12, minus 4 pi on 12. And this is how we find our intercepts when we have a transformation in the y-axis. So now I can simplify these. Negative 3 pi on 4. Negative, it's going to be pi on 4. It's going to be pi on 4. And that's going to be 3 pi on 4. And now I can kind of see where the pattern's happening. So I know that that graph, the original one that we had, is sine. It's been shifted up by a half, don't forget, and it's been translated across. So now when you graph it, you can still use your original thinking, So, you know, we can actually still see that's been translated, but I know that my y, when we shift it up by a half, that my intercepts are going to actually occur at negative pi on 4 and pi on 4 and negative 3 pi on 4. So when you shift it up a half, it's actually going to be, you know, intercepting at different points instead. And that's how we can get there. That's pretty much where we're going as a general overview of the whole sub-chapters of the next 3. And that's why where we're trying to go. So if we want to find solutions for this when x sine theta equals a half, we've got a domain. Now, this hasn't been dilated, so hopefully you know that the period for this is normally 2 pi, right? It goes 0 to 4. So really, all we can think about is you can think about, okay, when sine half equals a half. If you think about when it equals a half, well, it would be here, 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 and here. Or you can think about it in terms of the unit circle, but hopefully thinking of terms in both. So, I mean, if you think about that in terms of the unit circle, when does sine equal a half from 0 to 2 pi? Well, a half would occur here and here. So it's going to be a pi on 6, 5 pi on 6. Keep on going. That's going to be 12 pi on 6, 13 pi on 6, and that's going to be 18 pi on 6, 17 pi on 6. So you can think of it as that as well, which would get you there. Alternatively, you know that like what happens is because on the graph it's going to be here and here, right? So you know it's going to be at pi on 6, and you also know it's going to be 5 pi on 6. And the next time it's going to hit that is 2 pi on that. So I just need to add 2 pi to both of these. So if you think of 2 pi in terms of 6, that's going to be 12 pi on 6. So if I go pi on 6 plus 12 pi on 6, I know that's going to be the next time because I'm starting here, and what I've done is I've just added a whole revolution on. Here, I'm starting at 5 pi on 6, which is there, and I'm adding another whole revolution on. So you can actually just see that you can add increments of its dilation. So that's why we're adding on the 2 pi there to help us think the third and fourth solution to get us into the domain. When we sketch it, we can also see that there's 4. You know, if you think of the graph of that, you can see there's going to be 4 intercepts for that there. Find 2 values of x when sine x equals negative 0.3 with 0 to pi. So if you think about from 0 to pi, when it equals negative 2.3, it's going to have to be the y. So there'll be 1 here and 1 here. And that's where you'd go with that one. Sorry, I just got to check if it's all, yep, that's all good. So what we can do there is we understand the area for that, 0.3. So we can actually get, you know, we've got to use our calculator there to help us get to pretty much what that is. And we can find out what the values of the solution is there. So sine theta is 0.3. So you'd use your CAS on that one, right? So you do inverse sine 0.3. When my CAS wants to come up. There it is. So main, clear all. So I'm just going to literally bring up my keyboard, trig, sine. No, I don't want to find the angle. Yep, sine 0.3. We're trying to find in terms of in radians. There we are. So sine 0.3, because we want to find out what that is. That is 0.3 radians, because remember, that's the height, which you're going to get there, 0.3. So that tells me how high, what we are. Then I've got to add on, in terms of radians, pi to that, and you'll get pretty much what it is to get to the other side. Why are we doing, remember that's only from 0 to pi on 2. So you find the solution. So we do have some symmetry relation. That's for this one, sine, when sine equals negative 0.3 from 0 to 2 pi. So it's going to be negative 0.3 from here and here. So you know if that's 0.3 here, where it is, you can add on pi from here. And that will get you to the third quadrant. If you're from x, what we can do is we can go, well, 2 pi, which is a full revolution, and we can also minus then the angle as well. So that's how we're trying to find what the value of these two are, because obviously we're looking for negative 0.3. So if you think about what 0.3 is, it's here. Therefore, you'll get to both of these points there. So you need to think about what's happening in the unit circle for those 2 points to get to that solution. So now I've got my 0.3 here. Basically, if you think about where negative 0.3 is, if it's between 0 and 2 pi, well, I can go pi plus this, because that would take you pi plus here, or I can go 2 pi minus this would get me to there. And that's what we're doing. And they're pretty much the same one. This is in degrees, obviously here, so you just got to be a little bit careful. We're looking for degrees in there, so we need to just convert that across and make sure you're actually doing it in degrees instead of radians. So you'd obviously just go cos, inverse cos, because we want to find the actual angle. Just change that to .79 is what it is. Times by, what are we talking about? Pi on 180, right? No, I didn't do that right. What do I want to do? Cos, inverse cos, that's what I want to do. Do that as not complex, as degrees. Sorry, do that one as degrees is what I should have done first off. 45.7, because we're in degrees. That will give it to you straight away. Looking at the next one, we are finding the values of theta between 0 and 360, for which equals cos pi equals root 3 on 2. If you think about root 3 on 2, that's the 60 degree, or the pi on 3, 1. So you know cos, if you think of the unit circle for that, or you can think of the graph either with those. But obviously cos 3 pi on 2 is going to be here, and it's also going to be down here. If you think of graphing cos, cos is the x-axis, so it actually starts at 1, goes down, back up. So that's a cycle of cos with no dilation, reflection, transformation. So if you think of where root 3 on 2 is here, and it also occurs again over there, which is on the unit circle, which is here and here basically. So this should be a bit familiar with you guys. You should hopefully know where the values are for these and just basically locating them around and using that unit circle to help you get there. When we're solving these equations which actually have dilations, this is where we're going a bit different before. So I will quickly run through this. So instead of trying to solve this for 2 pi, you're just going to write this, you're going to let x equal 2 pi. So that's what we've done here. We're going to let x equals 2 theta, I should say, sorry, not 2 pi. So then you're just going to solve it for sine x, and that's all you're doing. So let's go through this example with you guys. So solve for negative root 3 on 2. And this is why we're doing it in here, because I find sometimes it's a bit removed. But why we're doing, we let this equal 2x is for what I showed you earlier when you have transformations in the y-axis. So sine equals 2 pi equals negative root 3 on 2, right? So we're going to let 2 theta equal x. So really what I want to do is I want to solve sine x, right? Equals, when does that equal negative root 3 on 2? Well, hopefully you can come back to the unit circle. We know sine's the measurement of the y, right? That is going to be, I did stuff up before, I think, with cos. Cos root 3 on 2 is going to be 30 degrees. I think I said it was, yeah, it is 30 degrees. I think I said it was 60 on my diagram. Sorry about that. Sine 3 on 2 is 60 degrees, right? That's up here and up here. Yes, I think my diagram wasn't right before. But we've got to be negative. So it's going to be in these two quadrants down here, okay? So that's going to make an angle of pi on 3. This is going to make an angle of pi on 3. So do we have a domain to deal with on this as well? Right, from negative pi to pi, right. So if you think about the graph of what I'm actually doing here, if you think about this graph here, if you just had sine theta or sine x, that would be starting at 0, and it would be pretty much like that for the domain, right? But this 2 is going to dilate it, right, by a half. So what it's really going to do is it's going to take in this point from here will become pi, because at the moment it's minus 2 pi if you're just doing sine theta. But when I do sine 2 theta, that's going to become minus pi, right? So what a trick here to do is with your domain you times it by the period out the front. So because I know that my domain is negative pi to pi, and what I have is I've got no transformations, but I have a dilation of 2. So because it's going to shrink it by 2, I need to increase my range by 2 because I know that's going to be shrunk. And that's where some people get a little bit confused. So I've actually got to list down all the values for this between negative 2 pi and pi. Because when you actually think of what this graph would be like, it would be from here is what's going to happen, because that's going to be pi, and that's going to be negative pi, and that's actually going to be pi. But because I've just let this equal 2x, this 2 theta equal x, I'm going to divide by 2 later on. It's going to move everything down. So I need to actually make my domain when I'm listing out these values from here, not from the original one, because I haven't taken my dilation into consideration, but I will later. So I know what's the values of x going to be when it takes on this value between negative 2 pi and 2 pi. Well, again, it's going to be here and here. So negative 2 pi would be all the way around. So if you think about the very first one, well, that'd be negative pi and 3. That'd be negative 2 pi and 3. So that would be the very first one. The second one would be negative pi and 3. Then you're going around to 2 pi. 1 pi, 2 pi, 3 pi, 4 pi and 3. 5 pi and 3. So they're all my values. Now, you'll notice, remember, we let x equal 2 theta, right? And this is what I'm trying to explain a bit earlier. We actually know that 2 theta equals these angles, because we've just, that was what it was before. And now watch this. Now I'm going to divide everything by 2, right? And that is now going to make 2 pi on 6, negative pi on 6. That's not negative. 4 pi on 6 and 5 pi on 6. So now my dilation I've applied to all of these, right? And now you'll notice they fit in the original domain. So a trick there is whatever your dilation is in your y-axis, you multiply your range by. Also, if you know where it's going to be transformed, right? So just say it was like 2 theta plus pi on 6. Well, if you think about the graph, right? If you think about this graph, the graph itself is going to be dilated, and then it's going to be all shifted across pi on 6, right? And it's going to go to the right. So if it's all going to move to the right, what are you actually doing to your numbers over here? Like everything's going to move that way, right? Like it's going to be that way when you do it. So really, if you're going to move it that way, your whole graph, you're really going to be using more like a section like this. Now I haven't calculated, but just for example, so it's going to go beyond. So what I need to do is I actually need to add pi on 6 to all of these ones here. Okay, so I need to add pi on 6 to that to then figure out what my domain is going to be. Easiest thing is just go a little bit beyond on both ways and you'll list them all in. So that's where we're going. So that's how you get the solutions of those. And that's pretty much it in a nutshell. and how we can get the solutions for those for them. So you'll find that that will work. And then always don't forget to simplify your answers where I didn't, because that's what you should do. So theta equals negative pi on 3, pi on 6, 2 pi on 3, 5 pi on 6. There should be a comma. Hopefully, and that's how you get your solutions. And that's how we'll be doing it by hand. So that's the tricky part. It does take a while, as I said, but pretty much that's what we'll be doing for the whole of these sub chapters. You'll either be, find these generic solution comes more in handy. You can still use it for either of them, but you definitely need to use this technique when you've got translations in the y-axis. Luck. I hope that helps you a bit with your explanation. And we're just going to work through some questions.